vectors. So those of you who have taken physics already know what a vector is, and you have a good idea of what we're going to be doing. When we do the math portion of it, it is a little bit different. It's very simple math, and we don't get too involved in the physics, but there are a couple of concepts that are physics-based, okay? And we'll talk about them when we get there. Okay, so what are we going to be using in this chapter, or really throughout all the chapters in vectors, is the Pythagorean theorem, SOHCAHTOA, the sine law, the cosine law. So just by looking at the topics that we are reviewing, you should realize that we're going to be dealing with right angle triangles, yes? Or triangles in general. All right, so let's talk about direction. So due north, everyone should know that's due north, right? When we say due north, that means that you're heading towards north. It means you're actually coming from the south, right? So you're coming from the south towards north. Good. 20 degrees east of south. So hold on a second here. For some reason, my PDF is not cooperating with me. Okay, let me just draw it. So if we're talking about 20 degrees east of south. Well, here's your compass. And we're starting from south, and we want to go 20 degrees east. Okay, so 20 degrees towards east. So that's 20 degrees east of south. Okay? Now, a bearing of 120, when you're talking about bearings are a little bit different because we start 0 here. Oops. Come on. 90. And we keep going from here, right? So 180, 270, you guys know. Okay. So 120 degrees, you're always measuring from north, and you're going in a clockwise direction. So 120 would be between 90 and 180. Okay. And that's why we see it there in quadrant 4. 120 degree angle in standard position. So this is our standard position. I'm looking right here now. So standard position is different. We start 0 here, 90, 180, and 270. And then we're back to 360 here. So standard position, we always work in a counterclockwise position, starting from 0. And so 120 degrees would now be in quadrant 2. It is very important that you understand the differences in the way that we talk about direction. Okay, because as you can see, the drawings will differ. Are there any questions about this? Good. Oh, yeah.
Can you explain the bearing one again? Bearing of 120?
Yes. So whenever you're doing a bearing, so now you're starting your 0 degrees from north when you're talking about bearings, and you're moving in a clockwise direction. So just move 120 degrees to the right, and that's why it brings us between 90 and 180. Do you see that? It brings us 30 degrees, okay. Right? So that what this is telling me is that I know that this little angle here is 30 degrees, right? And you know that this is 90. You see that? So that's a bearing. So bearings are always like this. And in the question, you'll be told, you'll see whether the direction is written like this, or it's going to say a bearing of, okay? Or an angle in standard position. So you're not going to have to guess, but it will be in the question which one you need to use. Okay, so a quantity that can be represented by a single number is called a scalar. So for example, when we talk about speed, we say 500 kilometers per hour. We don't care about the direction. And so that's called a scalar. Where a vector is now when we're talking about a quantity and direction. So we're talking about the magnitude, the size, and the direction. So the example now would be, if you're talking about velocity, you're not going to just say 500 kilometers per hour. You're going to give a direction. So 500 kilometers per hour in southwest direction, right? Which means 45 degrees between south and west, right? So that's the difference between a scalar and a vector. Okay, so a vector has both magnitude, which just means size, and direction. Vectors can be represented geometrically as a directed line segment. So they have an initial point, we call this the tail. And a terminal point, we call this the tip. Okay, so you're starting from the initial point, moving towards the end point, the terminal point. That's where you end up. Okay. Vectors can be represented algebraically as an ordered pair or triple. So obviously this is in 2D space, this is in 3D space. A comma B is going to tell us the direction, okay, or where our terminal point ends up. So for example, in this case up here, I've moved A units to the right and I've moved B units up. Do you see that? But these are now vectors. Okay, so that's how our components are going to work, and we'll talk about that. So various symbols can be used to represent vectors. So as you saw, I just used this form. So vector A, it's got an arrow on it. A lot of times, guys, when you write it, you write it like that. Okay, and you'll see that in print as well. Capital AB, this is just showing, so let's say, for example, this is vector AB. So you're going from point A to point B, and it gives you vector AB. And then you'll see bolded. Okay, now that's only good for text. I don't want you guys to be bolding because I can't tell. So, right? So I need you guys to use arrows.
Miss, I'm here.
Oh, who's here? Oh, that's Nigel. Nigel? Okay, hold on. I gotta fix the comments. Thank you. What about Radine? Did Radine show up? No. Okay. Okay. So where was I? So there you go. So you guys always have to use arrows. Always, always, always. Now, if you want to know the size of a vector, then you're going to find its magnitude. And the way that we know we're talking about the magnitude or the size of a vector are the absolute value bars. These absolute value bars tell us that we want just the length of it, just the size of it. So obviously we don't want any negatives in there because we're talking just about size. So this is should make sense to you because you know what absolute value bars are. And with absolute value bars, you always just take the positive, yes? And so this is the exact same thing, okay? It's the same concept. Here we have the absolute value or the magnitude of vector AB. That means we want to know the length of that vector. And then here we have the absolute value of that bolded vector U. And again, we just want to know the absolute value of it, the size of it, okay, the length of it. So for example, if I have vector A and its components are 5, 0, well, that means that I've moved 5 units on your x-axis, no units on the y-axis, and so this is my vector A. When I'm talking about magnitude, the magnitude or the length of this vector would be 5 units. Okay, are there any questions? Okay, good. The opposite of vector AB is vector BA. So, are they the same? Well, they have the same magnitude, but they are not the same vectors because they go in different directions. Okay, so vector AB goes one way, BA is now parallel to AB, okay, but it's going in the opposite direction. The opposite of vector U is negative vector U, and again, it's the same concept. If this is U, then negative U is parallel to it, but it runs in an opposite direction. Note that AB and B is parallel to BA and vector U is parallel to vector negative U, as I just showed you. The angle between two vectors is the angle formed when the vectors are placed tail to tail. Always, 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 always. You can't place a vector from tip to tail if you are talking about the angle between them. Okay, so whenever we're talking about an angle between two vectors, it's always going to be when they're placed from tail to tail. Okay, so both of their tails are touching. Okay, and then obviously this is the angle theta that we're talking about. Okay, so when are vectors equal? Vectors U and V are equal if and only if they are parallel, they have the same magnitude, and they have the same direction. As I've already stated to you before, if they're in opposite directions, they are not equal. Okay, just a little side note, if and only if no one's ever told you this before, is very commonly used in higher mathematics. And what it means is you can go both ways. So this is the symbol for if and only if. So what that means is, if I tell you that two vectors are equal, then you already know, you can assume they are parallel, they have the same magnitude, and they have the same direction. Or I can tell you, two vectors are parallel, have the same magnitude, and have the same direction, and then you can conclude that they are equal. Okay, you can go both ways. Does that make sense to you guys? That's different than an if-then. An if-then only runs one way, and that means that A has to happen before you can conclude that B is true. So that's the difference there, just a little bit of math terminology. Cool? Cool. Okay, vectors are not stationary. What does that mean? It means we can translate them anywhere. We can move them anywhere. So to understand how to draw them, well, we're always going to have them at the origin here. But then we can displace them wherever we want. Okay, so this is vector A, and so this is vector A, so is this, and so is this. And they're equal. And they're equal because they're parallel, they have the same magnitude, and they have the same direction. Doesn't matter that we are not positioned in the same place. Okay, 6.2, vector addition. So that was 6.1, very quick. Do you guys have any questions? Okay, so let's talk about how do we add vectors together. So when you're adding vectors together, well, we want to follow a path. So vector A plus vector B. So here's vector A. And now we want to add vector B to it. So we literally, it's like we're just following a path. Okay, that's how you add vectors together. So what's the point of doing this? Well, you get a resultant vector. So now you get a resultant vector, which is called vector A plus vector B. Do you guys see that? Okay, this is your resultant vector. Notice it starts where you started and it ends where we ended. Okay, where our path ended. This is called the resultant vector. This is called the triangle law of addition. Okay, why? Because we formed a triangle. There's also a parallelogram that I will show you. Okay, a parallelogram law of addition that we will see. Okay, recall from triangle properties that this length, so vector A plus B, the length of that is less than or equal to vector A plus vector B. Okay, so this is always shorter, and we know that, right? We've seen that many times before. Okay, example 2. Given vectors A and B, sketch A plus B. So A and B right now are shown tail to tail. This is how we place them when we're talking about the angles between them. But we don't care about the angle between them. Right now we want to add them. So what I need to do is I need to take that vector B, and I need to displace it and put it here. And so now, for me to get my result, that's my resultant vector. Okay? And it's showing it right here. Okay, now, this is the this here illustrates the parallelogram law of addition. And what's happening here is you notice that we form, if I were to bring A here, and I have B here, then you can see that we have the exact same resultant. That's actually not true. Hold on, that's not what I meant to say, because we would not have the same resultant, right? We know that this is a different resultant. Sorry, what we're seeing here is that we can form a parallelogram by joining the exact same vectors. So here we have vector A, here we have vector A, here we have vector B, here we have vector B. And we can then conclude, or we can use our Z law to find angles. I can conclude that this angle is equal to this angle. I can use a C pattern saying that this angle plus this angle will equal 180. I can also use a C pattern saying that this angle plus this angle will equal 180, and we can use all of our geometric properties. Okay, so parallelogram law of addition. Okay, example 3. Given vectors A and B, sketch A minus B. Well, it's important to note that A minus B is really just vector A plus negative B, right? Vector negative B. So having said that, here's vector A. Here's vector B. If I want negative B, I know it has to have the exact same length. Oops, that's terrible. It has to have the exact same length. Let's see if I can do it this way. Oops. It has to have the exact same length, but run in the opposite direction. And so now, if you're doing A plus negative B, well, again, I have to take this vector. Oopsies. I want to take this vector and I want to displace it. I'm going to put it here. Don't forget the arrow. And this is now negative B. So now the path that we're following, let me get my highlighter, if I can get it. Okay. This is now my path. So that means that my resultant now will be there. Okay. So that's vector A plus negative B. And here it is right here. So here's my vector A, here's my positive B right there. There's my negative B. It's exact same size, but running in the opposite direction. And then I displace it to here because we're adding. And so we have to always bring our vectors together like we're following a path. Okay, I'm going to just put you guys on a quick hold. I'll be right back. I just need to get my kids in from outside, okay? Because they have to start school too. Give me 1 second. Okay, I'm back. So let's go back to our slide. Sorry, guys, I had my kids playing in the background for like a little recess just to get them some fresh air. And now they're coming in. I just had to call them in. Okay, so where were we? All right. So are there any questions? Do you guys understand how I got A minus B, vector A minus vector B? We just added B. Yeah, talk to me.
Yeah, compared to example 2 and example 3, right? We are doing like it does not make so many sense.
It doesn't make sense to you?
Yeah, because examples 2, we are adding 2 vectors together. However, the B is.
So look. Do you see that?
Right, I got it.
Okay.
Yeah.
Now you're okay?
Continue.
Okay, so now here's vector A.
Yeah.
And I need to add negative B. So this is positive B.
Right.
In order to get negative B, we have to put it in the opposite direction. And now it's like I cut and paste it. I displace it and I put it here. Now, your resultant vector is always going to be where you started to where you ended. So I started here and I ended here. And so that's my resultant vector. So I'll say it again. The path we're following, here's my vector A, and now I want to add negative B to it. Well, negative B runs this way. And so now my resultant is from where I started to where I ended.
Right, but didn't negative b is at bottom of the vector A?
Yeah, but you can move them, right? Vectors can be moved. You can
Sure.
move vectors wherever you want. So what I did was, it's like I cut and paste. I took this vector, and I put it here.
Ah. So why in example 2 we did not move it?
We didn't have to. We didn't have to. Look, so here, let's go back. So here, it was just A plus B. I didn't have to do anything. See this vector, and in fact, I did move it. See how B is here?
Yeah.
Look, B is here. I displaced it to here.
Oh, okay, got it. Thanks.
Yeah, no problem. Cool?
Cool. Thanks.
Okay, no problem. All right. Okay, now, example 4. Express each of the following vectors in terms of A, B, and C. So we're going to start with vector FE. So it's important to understand what vector FE is and what direction it goes. So here, highlighter, this is vector FE, and it has to go in that direction, like this. Okay, so now, in order to describe vector FE, how can I describe FE? What does it relate to here? Does it relate to B, C, or A? What do you guys think? A, good. It's the exact same vector like A, except what? How are they different?
Direction.
The direction is different. So I'm going to call this negative A. So vector FE is equivalent to vector negative A. AF. Okay, so now AF. So AF is this. So now, how can I describe vector AF? In this case, we're given a resultant. Do you guys see that? AF is a resultant. So what path can I take to get to F? Well, I got to start from A. So I could, let me get my highlighter. I could go this way. And that means I'd have vector A plus vector C. Vector A plus vector C. Or if you wanted, you could have gone the other way, which would have been vector C plus vector A. And these are the same thing. Okay, this is a commutative law, so it doesn't matter which way you write it, it equals the same thing. So I could have, with my highlighter, let me get a different color. I could have gone this way. But the result is still the same. 1 second, sweetie. Sorry, guys, give me 1 sec. 1 second, please. Thank you. 1 sec, guys, I'll be right back, okay? Okay, guys, sorry about that. All right, let's get back. Okay, so are there any questions? Is everyone good with this? All right, so
Miss-
let's do the rest. Yeah, tell me.
Radine is here, I think.
Oh, thank you. Radine, you around?
Yo.
Radine, okay. You gotta tell me when you come in so I can change the attendance, right?
Oh, my bad. I didn't even know there was attendance.
Yeah, always, every day. Okay. So let's go back to here. Okay, all right, so BE. So BE, let's take a look. So BE is now the other way. It's that guy. Oh, that's horrible. That's my BE right there. So you guys tell me, how am I going to get to E from B? What's the path I'm going to take?
Vector C plus or minus vector A.
Good. We're doing negative vector A plus C. You're right, which is the same as C minus A. Okay, good. Now, that's not the only path. I could have also gone the other way, or I could have, if I really wanted to, gone up to C, across to D, come down, and then go across. I mean, you can do tons of things, right? But you want to be the most efficient. Okay. All right, AG. So from A to G, what path are we going to use to get there? What do you guys think?
A and B and C.
Good. You have to use A, B, and C. So we're going to do A plus B plus C. Very good. And it doesn't matter which way you write this. Again, it's a commutative law, so you can write them in any order. Okay. Okay, FD. Let's take a look at FD. So F going to D. What path do you guys want to take?
So we're gonna take B and then we're gonna manage vector C and vector A, right?
Okay, good. So we noticed that we're going to have a negative C, we're going to have a negative A, but we're going to have a positive B. And so we could write it like this, or better yet, okay, both are correct. Any questions? Okay. Example 5. Two vectors A and B make an angle of 30 degrees with each other. Okay, right away. We're talking about two vectors making an angle. So that means I need to draw these vectors tail to tail. That means both arrows are away from one another. And it's got to be approximately 30 degrees. And I don't care which way you draw this. It doesn't matter how you draw this, as long as the angle looks like it's approximately 30 degrees. It's not going to be exact, but we know that it's acute, correct? So I could do it like this. So notice that the angle between them is 30 degrees. If the magnitude of A is 3 and the magnitude of B is 5, calculate the magnitude of vector A plus B, so of the resultant. Now, in order for me to find the resultant, I have to have them like this. Why didn't I mean to do that? So this B now has to go here. It's the exact same vector and it's the exact same length, but because now I'm adding, in order for me to get my resultant, I must do it this way. But that 30 is still going to help me because as we saw before, I can form a parallelogram, and then I can find all the angles I need to solve this problem. So this is A plus B, and I want to find the magnitude of it. So what are you guys thinking? Do you see something here? Does anything jump out at you?
C pattern.
Yeah, good. So what you should see is, well, I need to solve A plus B. I know that the length here of B is 5, and I know that the length here is 3. However, that angle 30 isn't doing anything for me. So instead, I want to use this triangle. And I want to use that 30 to help me solve this. And this is what we're looking for. The magnitude. So if I know that this angle is 30, I can use the C pattern to find the angle I need. And the C pattern tells us that these two angles must add up to 180. And so I know that that must be, oopsies, I know that that must be 150. Is everyone following? So I'm using the C pattern to get the angle inside the triangle that I want. Okay? And now from here, it's easy. What kind of a law can I use to solve this? It's not going to be SOHCAHTOA. It's not a right angle triangle. But what can I use here? I've got two sides and I'm looking for the third side. I've got the two sides and the angle between them. So what can I use?
Cosine law.
Good, we're going to use the cosine law. And so using the cosine law, we know this is the cosine law. And yes, you must know your cosine law and your sine law. Okay, so what I want you guys to do is right now solve this, and I will be right back. Tell me what you guys get. So Stephen, take a look here. Let me go back to it. So take a look here. So I know it's very messy. So we had this angle 30. I'm going to use my highlighter. Okay, 1 second, Christian. I'll be there in 1 minute. 1 minute. So now, here. Do you see that, Stephen? Do you see how we formed a C? And I know that those two angles, those two interior angles in the C pattern have to add up to 180. So that's how I know that that angle is 150. Do you see that? Okay, good. Perfect. Okay, guys, I'll be right back. Solve that. Tell me what the answer is to 2 decimal places. Okay, so what did you guys get? Using the sine law, what did you guys get? Oh, sorry, cosine law, excuse me. What did you guys get?
About 7.74.
Perfect. Okay, approximately 7.74. So remember, guys, you're looking for A plus B, so you're going to take the square root of everything here. We know that the magnitude of A is 3. We know that the magnitude of B is 5. This is still under my root. Okay, make sure you calculate it in degrees. And you're going to get approximately 7.74 units. Are there any questions?
Miss,
Yeah.
when you find the 150-degree angle, can you use
Yeah.
like the Z pattern too? Or do you want us to specifically use the C
Oh,
pattern?
no, it doesn't matter. You use whatever you have to as long as it's legit. As
Okay,
long as it works, it's fine. You can use so many different ways.
thank you.
No problem.
Do you
Okay,
have to show work or can you just write the
you do
angle?
have to show work. Yes.
The C pattern?
Yeah, so you guys have to state what you're doing. So, yes, I want you to tell me what you're using, how you found your other angle, and I want to see both of these drawings. So both the drawings that I have here, I expect you guys to show me on a test. Okay?
Okay.
Okay. Now, example 6. An airplane heads due north at 500 kilometers per hour and encounters a wind from the west at 100 kilometers per hour. What is the resultant ground velocity of the plane? Okay, guys, so what does this mean? Resultant ground velocity means we want the length of the resultant vector. So what I want you guys to try doing is come up with a diagram for this situation. Just take a minute and try to come up with a diagram for this situation. So it says an airplane heads due north. Simple enough. Airplane is heading north. We'll use a P because it's a plane. And then we have a wind from the west. If the wind is coming from the west, that means it's actually traveling east. And this is where students get confused. So your drawing should look like this. It should not be pointing towards the west. It should be pointing towards east. Okay, and that's the only trick to this question. What you should realize is that we have formed a right angle triangle. That's my resultant vector, and so I use R. So here's my right angle triangle, which is simple enough. I know the magnitude of the plane. It's 100. Oh, excuse me, it's 500. I know the magnitude of the wind. That's 100. And I'm looking for the magnitude of the resultant vector. So what am I going to use here, guys? Is this hard math? What are we going to use here to solve for R?
Pythagorean theorem.
Pythagorean theorem. Very simple math. Please notice the notation, guys. I do expect you to use this notation. Solving for the magnitude of R. I have 500 squared. That's 100 squared. And you can go ahead and give it to me to one decimal place, please. Tell me what you guys get to one decimal place.
509.9.
Good. Excellent. So that's giving me my kilometers per hour. Now, they didn't ask for speed. They asked for velocity. And that means that I need to find a direction. So if I'm looking for a direction, well, that means I need to find an angle. So what angle am I looking for? Well, the plane was traveling here. That's what it was doing. The plane was traveling here. But then a wind came and pushed it. And now the wind is going this way because the wind pushed it that way. And so the angle that I'm looking for is the angle that it changed. How did the direction of the plane change? That's how the direction of the wind changed. So to find that angle, again, using very simple math, what am I gonna do?
SOHCAHTOA.
SOHCAHTOA. And if it's SOHCAHTOA, I've got my adjacent, I have the hypotenuse, I've got the hypotenuse. So what am I going, sorry, I've got the opposite, I've got the adjacent. I've got my opposite, I've got my adjacent, I'm going to use tan. Notice, guys, we always use the information that we're given rather than what we solved for in case we made a mistake, and also because we've approximated. And so I want to know the angle, and so I'm going to take the inverse of tan in order to solve. And again, make sure you're in degrees. And what's our angle theta?
About 11.31.
Sure. So I'm going to just round it to 1 decimal place. And I've got approximately 11.3 degrees. And of course, guys, we need a statement here. So therefore, the plane is flying with a ground velocity of 509.9 kilometers per hour, but I need to talk about a direction. So we know it's 11.3 degrees. In what direction is it? How would you describe that?
North 11.3 degrees east.
Okay, good. So it's east of north. Perfect. And that's exactly how we write it. We write the north first because it's east of north. So it's 11.3 degrees east of north. East, you guys can see that this way is east of north. Are there any questions? Okay. So very quickly, let's look at the properties. So what's a commutative law? Commutative law in math is when it doesn't matter the way that you are adding your vectors together. It's not just for vectors, right? I'm sure you've heard this word before, the commutative law. It's the same thing as 3 plus 2 is the same as 2 plus 3, right? That's a commutative law. So here I have vector A plus B is the same as vector B plus A. Associative law. So now I have 3 vectors that are all being added together. It doesn't matter which 2 vectors you add together first. Okay? So this could also be equal to B plus A plus C. And the A plus C is in brackets, right? That would also be equivalent to my 2 expressions there. So properties of the 0 vector. The 0 vector is represented by a 0 with an arrow. If it doesn't have the arrow, it's not a 0 vector, it's just 0. Okay, so it's very important that it has the hat on it or the arrow on it. Its magnitude is 0 and its direction is undefined because it's nothing, right? It's 0, it's a nothing vector. But the reason that we need a 0 vector is because if we are adding A and negative A, then we can't say that it's just 0 because that's not correct. If I'm adding 2 vectors together, the result has to be a vector. And so we need the 0 vector. Does that make sense? If I have B plus negative B, right? Or excuse me, vector B plus negative vector B, well, that can't just equal 0, it equals the 0 vector. Okay? And this is your homework, guys. I've made some notes here. So 6E, there is a typo. And also, yeah, in the answer. I think the answer is incorrect. Hold on a second here. Let me see. So 6E typo. And then I have in my notes, it says answer incorrect. Here, I think the problem here is it's supposed to be east. Like so. And then there's also a typo in question 10. So for 10B, this is missing. The squared is missing. Okay, so be careful. Okay, and I'm sure, oops, missing. Okay, So that's the homework for 6162. So we're also going to do 6364. We're just going to take a quick little break. You guys can get up, shake your legs a bit, and then we will start the second lesson in about 5 minutes, okay?